who will be very happy to answer all questions. I didn't really plan for 50 minutes, so I do hope there will be questions. I desperately hope there will be questions. The title of the talk is a bit of a mouthful, a simple condition for constant regret in online decision-making. I actually want to replace constant regret by uniform loss. Sid prefers the regret language. I'm a little bit hesitant to use the word regret because then people think of bandits, and this is not about bandits. Now, it is about online decision-making, and I sort of want to say pick your favorite online decision-making problem. So online bin packing would be one problem that we can tackle using our sufficient condition. Online network revenue management would sort of be the one where the idea originally came from in a former paper of Sid's. We're going to have a running example of an online job allocation problem that I'm going to define in a little bit. All of these very, very easily fall into the framework that I'm going to describe. Now, the online decision-making world that we're living in is one with a long but finite time horizon. And in each iteration, there's some random arrival. Right now, I assume that I have coin tosses, but they don't need to be coin tosses. It's just some type shows up in each iteration. And I know the distribution that shows up. And I then need to take an action that, again, right now I assume there are just two actions. There can be any number of actions. And in the end, at the end of the time horizon, we're going to have a function f that we're trying to minimize. And f is a function of all our actions, but it's really just a function of how often did we take each action for each arrival type. So if you think of the action being either accept or reject, then I don't care when you accept it or when we accepted a particular type. I only care about how often did we accept each type. Now, what is our benchmark? What do we compare ourselves to? As I said, we know the distribution of arrivals for each of the independent arrivals that occur. Our benchmark will be the clairvoyant offline optimal. So we compare ourselves with somebody who knows the exact outcome, who knows the exact arrivals that occur in every single iteration. So this is sort of an MDP setting. It's not, as I said, any sort of bandit or adversarial setting. But I do want to highlight that our offline benchmark here is better than the optimal solution. So the optimal solution still needs to somehow cope with the randomness that occurs in the problem, whereas our benchmark actually doesn't need to deal with randomness. Our benchmark knows exactly what's happening. So we want to get uniform loss. So we want to minimize the expected difference, expectation being taken over the random arrivals, of the objective value that the algorithm gets. We're not going to define our algorithm for a very long time, but we want to minimize the expected loss between the algorithm and the clairvoyant offline optimal. And when we say uniform, what we mean is we want it to be independent of the time horizon. Now, the piece I want to highlight is, even with infinite computing power, it's not a priori clear that this would be possible. So given that offline is a better benchmark than the optimum, even if you ignore any sort of curse of dimensionality, even if you ignore the fact that we may not be able to compute the optimum, we would still not necessarily be able to get a uniform loss, simply because our benchmark is quite a bit stronger. So in the landscape of online decision-making problem, we have the optimistic extreme, which would be the proximate dynamic programming, reinforcement learning. We can learn optimal policies using huge amounts of data and computation. And on the other end, we arguably have the pessimistic extreme that we can't use that we don't have any historical data at all to learn from. And we are in the adversarial context. We are really in the middle ground where we have data to base it on, but we don't have the infinite amounts of data. So our informal result is then, and this is really a very informal way of stating it, as long as f fulfills some regularity conditions that we're going to get to, then there exists an adaptive algorithm that obtains uniform loss. Yes?
Sorry, I'm missing something about the setting. What is the information I have when I make this decision?
Sorry, yes. That is, thank you for asking, because it's super important that this is clear. You know the types that exist, and you know for each iteration the probability that each type will show up. So if you think about the distribution being IID, which it doesn't have to be, we only need independence, and even that can be relaxed somewhat. But if you think about IID, you know the probability of each arrival occurring. So you know type I shows up with probability 1/2, and type 2 with probability 1/3, and type 3 with probability 1/6. But the clairvoyant knows in the first iteration, type 1 shows up, in the second iteration, type 3, and so forth.
So before making my decision, I see the realization for today,
Yes.
and then there's some feasibility constraint on that couples the decision across periods and prevents me from just making an optimal decision in each period.
Either a feasibility constraint or something that is captured by f. So f needs not, yeah. Yeah.
The actions are either accept or reject. So actions are binary.
Think about accept or reject, but if you think about bin packing, there's no accept or reject. You can think about what type of bin do I want to put it in.
And f of x, this is the objective function, correct?
F is the objective function.
Yeah.
So, but you said f only depends on the number of times
Yes.
action. So how it can capture like this relation between, I don't know, like because you take the action after realizing the type, right?
So it works as follows. In iteration t, we see the arrival that occurs, and we then know the type. We then take an action for this type and this iteration. We don't know all the subsequent arrivals.
Right, but then f does not depend only on this number, right? The number of times you take action depends.
Think about x as being indexed. I should have said that more clearly. Think about x as being indexed by arrival type and action. So if we have type 1 and type 2 and accept and reject, then you should think of x as having 4 indices, one for accept type 1, one for reject type 1, one for accept type 2, one for reject type 2. Model clear so far? Okay.
And you're assuming f is convex.
And uniform is dividing by time, right? I mean, per time. Per time unit.
When I say uniform loss, no. I mean, my total loss can be bounded by a constant. And you just asked a good question. Can you ask it again?
Is f convex?
Oh, yes, great. No, I didn't use the word efficient in here. If f is convex, then I can actually give an efficient algorithm that obtains the uniform loss. So in order to, there's an information piece here where it's non-trivial, even if we ignore computation, that we can get uniform loss. In order to get something that's efficient, we need the convexity. We need to be able to compute an optimal solution to some offline problem that we're going to define. Now, there's a lot of related work in the last 2-3 years with people having found similar results for special cases of this. It's really most closely based to Sid's earlier paper with his student Alberto Vera, that was mostly looking at packing problems, and in particular network revenue management. And this is really where the idea is coming from. And I'm stating here the long literature on heuristics for network revenue management. But of course, there's much, much more that could be cited in this context, in this sort of problem being studied. Now, the running example that I promised I'd give is as follows. We have our T time periods, and in each time period, we get an arrival that is a dollar amount. Now, each amount is a payment, let's say a credit card payment, that needs to be sent to one of two firms for processing. So think your coffee shop, and people come in and make payments, and if they order just a coffee, then it's a $4 payment, and if they order a coffee and a pastry, it's an $8 payment. So each amount is a payment, and we need to decide whether we let Square or Stripe process the payment. The second firm charges just a constant fee for processing. So the second firm just says, every time a payment is sent to us, we're going to charge B dollars for processing this payment. The first firm charges a fee that's proportional to the amount that is being sent in this payment. But the first firm also has a lower bound of how much it's at least charging on average over the whole time horizon per payment sent to them. In a moment, I'm going to plug in numbers to make this a bit more tangible. So let's just say our arrivals, our payments are just $10 or $40. And we're in an IID case in which $10 in each iteration, it's a $10 payment with probability 2/3. It's a $40 payment with probability 1/3. Firm 2 charges $3 on every payment that we send to firm 2. Firm 1 charges 10% of the amount. So if it's a $10 payment, they charge $1. If it's a $40 payment, they charge $4. They charge 10%, but they also have a lower bound where they say, on average, you will need to pay at least $2 per payment that we process for you. So to give an example, if we send firm 1 5 $10 payments and one $40 payment, then we're going to have to pay the maximum of 10% of $90. 5 times 10 plus 40 is 90. And 6 times $2, because on average per payment, $6 were sent. 6 times 2, so it will have to be at least 6 times 2, $12. Now, one thing one can do, and that is sort of standard for this online stochastic decision-making approach, is to look at the certainty equivalent. So rather than saying $10 happens with probability 2/3, $40 happens with probability 1/3, we could imagine an alternate scenario in which we have things happen as an expectation. 2/3 of the time exactly, we have arrivals that are $10 payments, 1/3 we have $40 payments. Now, in that case, it's easy to find the optimal solution. And it would be route everything to firm 1. Why? Because if we route everything to firm 1, our payments will be, we can basically plug 2 $10 payments together with one $40 payment. Those are 3 payments of worth $60. 10% is $6, so we're paying exactly $2 per payment. We cannot possibly pay less than $2 per payment. So this would be optimal if we had the certainty equivalent, if we actually knew the things were happening as an expectation. So reasonable heuristic, the certainty equivalent control, is to say, ignore everything else that happens, and just assume things happen as in expectation and route accordingly. The problem is we get a loss, and this is from simulation, that increases with the length of the time horizon. And that's not super surprising. If you think about where does this loss come from, basically we're about square root t away from the expectation of what's happening over a length t time horizon. So we would expect the loss to grow in square root t. And the reason for that in this particular example would be that if we have $40 payments more than a third of the time, then for each one of these we're going to be paying $4 because we're sending it to firm 1. We would be paying just $3 if we were sending them to firm 2. Now, next well-known heuristic is the adaptive resolving heuristic. For that, we will need a little bit of notation. Think about Ni as the number of arrivals of each amount. So 10 times I. So N1 will be the number of $10 payments, N4 will be the number of $40 payments that arrive over the full time horizon. Ni of t is the forward-looking version of this. So in iteration t, of the remaining payments, how many are of value $10, how many are of $40? Of course, we don't know these. But for any sample pass, they exist. And yi will be our decision variable for the remaining time horizon. How many future payments of each value do we want to route to provider 1? And ai at this point is already constant based on the past history. How many payments have we routed of each value so far to provider 1? Now, the resolving heuristic tries to minimize over y, given history so far, given the decisions that were made and the arrivals that have occurred so far, and assuming that the remainder of time happens as an expectation, the total amount that we're going to be paying. Now, we're going to be paying $1 for each payment sent to firm 1 and $3 for each of the remaining payments in expectation sent to firm 2. For the $40 payments, we're going to be paying $4 for each one sent to firm 1, $3 for every one sent to firm 2. And now, this one here is a bit of a tricky expression. But basically, this says if in the end we're below an average of $2 per payment sent to firm 1, this is how much we're going to have to compensate to get to the right amount. I don't really want to go into the detail of where this comes from. It's not a complicated expression. But the interesting bit that the resolving heuristic then does is it says after each payment, route the payment to provider 1 or in the next iteration with probability based on the value of the resolving heuristic. So if we expect 100 payments of value $40 in the remainder of the time horizon, and we want 10 of them to be routed to firm 1, and now one of them shows up, then we're going to randomize with probability 10%, we're going to send it to provider 1, with probability 90% to provider 2. Now, this does a lot better. So again, this is simulated results. And we see this here was the loss of the static policy relative to the offline optimal. This here is the loss of the adaptive. And it looks like it's really staying very low. But if we look at a log-log plot, we actually see it's clearly increasing at the same rate in log-log space as the static policy. So we still incur a loss that grows in the square root of the time horizon relative to the offline clairvoyant optimal solution. what we're going to find throughout this talk is the policy down here that actually gets a uniform loss that does not grow with the time horizon, but not yet. First, let's think a little bit more about where the objective actually comes from, where the loss over the full time horizon comes from. And for that, let's think about defining an objective that is based on running t-1 iterations of the algorithm, followed by the remaining, and again, I haven't defined the algorithm yet, but we're going to run t-1 iterations of some algorithm, and thereafter we're going to let the optimal clairvoyant take over. Now, the pictorial description, I think, is better for this. So for the first t iterations, we're letting the algorithm do whatever it does, and afterwards, clairvoyant will try to optimize the remainder of time. Now, that lets us rewrite our loss as follows. The loss is the difference between algorithm and offline. Algorithm is the same as saying offline of t, running algorithm for t-1 iterations, and then letting clairvoyant take over. Doesn't help to be clairvoyant if there's only one iteration left. Whereas offline of 0, if we've run the algorithm for 0 iterations, then the clairvoyant is exactly the optimal. But that we can write as a telescoping sum. So we just have the sum over all iterations of the difference between what we would have had if we'd let the clairvoyant take over one iteration earlier or one iteration later.
So why don't you take essentially the loss instead of the minus? Why don't you take the ratio, expectation of algo over expectation of off? That's better things. And also, I mean, because like, additive doesn't mean that much essentially.
I claim that's trivial. Because if our objective grows as t, and even the static gets square root t additive loss, then square root t over t goes to 0. So getting a multiplicative error of 1 is just immediate.
But you have the same essential distribution that goes there. It's like that.
I don't know. You don't need IID for this.
Grows as t grows.
Yeah.
I think that's the essential.
The distribution.
If you consider profit, then you don't have such thing
No,
essentially.
so if ops doesn't grow with t, then profit inequality gives a trivial solution to this problem because any multiplicative is actually anti. That doesn't grow with t.
Okay. Now what I would love to be true are the following two properties. And those depend on the algorithm that I choose. But whatever algorithm I choose, I would love for it to be true. One, I don't want to ever have a costly mistake. What do I mean by that? Well, if you think back to the specific problem we're looking at, if we're sending one too many $40 payment to firm 1, or one to firm 2 that should have gone to firm 1, the cost was going to be at most $1. And the same is true for the $10 payments. So I want a bound over all possible states that we could be in the problem. Doesn't have to be 1, but I want to bound by a constant the cost of a decision of the algorithm that is not what the optimal clairvoyant wanted to do. And the second one, I want to be able to say with some high probability that actually the difference is 0. So if it's greater 0, I want it to be bounded. But with high probability, I don't even want the algorithm to do something that the optimal clairvoyant would not have done as well. This one in our case is easy. This one here, what does with high probability even mean? Well, what I really want to say is that over t iterations, I want the probabilities of this here occurring to sum up to a constant.
Not occurring.
Say again?
Not occurring.
Yes, sorry. The probability of this not occurring shall sum up to a constant. And those two very easily will give me uniform loss. Why? Because I can then say, well, sum over all iterations. This here, if it's greater than 0, then it's at most 1. And then I can just sum up the probabilities. And if those sum up to a constant, I've got uniform loss. So the name of the game is really, how do we know, how can we design an algorithm that will have this occur with high probability? How do I design an algorithm that with high probability gives me that the loss of a mistake, the loss of doing something that the clairvoyant would not want to do, is 0. For that, let's define the notion of a disagreement. So let's call an action of an algorithm a disagreement exactly if it causes the clairvoyant to have a worse objective if the clairvoyant is following that action. Let's get back to our specific problem. Suppose the amount in iteration t is $40. Now, if it's a mistake, if it's a disagreement, to send those $40 to firm 1, then it must be the case that clairvoyant wanted to send all remaining $40 payments to firm 2. Because otherwise, you could just swap around. Otherwise, you could just say, oh, actually, clairvoyant was going to send a later payment of $40 to firm 1 and not the next one. But we can just swap those two. And similarly, if sending it to firm 2 as a disagreement, then the clairvoyant must have wanted to never again send one to firm 2. It must have wanted to send all remaining ones to firm 1. So, long story short, the offline optimal to have a disagreement must have never wanted to take that action for the remainder of time. Now, for the specific problem, let's think for a moment about what the optimal solution looks like. The optimal solution is going to send all $10 payments to provider 1. Why? Because in the best case, it's $1. In the worst case, it's $2 to process a $10 payment through provider 1. And then it's going to send the $40 payments to provider 1 only to the extent that it gives us an average value of $2 among all the payments sent to firm 1. Which effectively means if there are more if there are more than 1/3 of the payments worth $40, then we send exactly half as many as we'd send $10. Otherwise, we send all of them to provider 1. Yes. So, let's think about the resolving heuristic again, but let's compare it to what offline of t does. So, we basically had the same notation before, except for I introduced yi star, which is basically the solution that offline of t is going to use. So resolving, we looked at before. I don't want to reintroduce it now. What offline of t, this was meant to be offline of t, not opt of t. What offline of t does is it solves the same problem, except for rather than having the expectation for each of the remaining arrivals, it has the exact numbers. And now we're getting close to actually the crux of what's happening. We want to bound the probability of a disagreement. And we're about to define the algorithm. Suppose it's the case that the remaining certainty equivalent in the resolving heuristic, the remaining payments that are being sent to firm 1 is more than half of the expected remaining payments of that value. What would it take to have a disagreement in the next in the next iteration when we're sending, this is meant to be a 40, when we're sending $40 to provider 1. Well, the offline solution routes all $1 payments to firm 1. And for this to be a disagreement, it must be the case that it sends all $40 payments to provider 2. Now, from the characterization of the offline policy on the last slide, we can get this inequality here that basically says the offline must be able to get to an average of $2 over all payments sent to firm 1 without sending any more. Now, we can rewrite that. Y1 we know is always all payments to firm 1, so that's just the expected number of these. And because we know that Y4 is greater than the expected expectation of N4 of t divided by 2, we get this inequality here. Now, this is basically a lower bound on the difference between N1 of t and N4 of t in expectation. Now, the question is, what is the probability of a disagreement? What is the probability of actually having a scenario where Y1 star, where Y4 star is equal to 0? Because Y4 star is the number of remaining payments being sent by the offline optimal to provider 1. If it's a disagreement, this here must be equal to 0. So the question is, what is this probability here? And here you should be able to see this should be exponentially unlikely by Hoeffding's inequality, because the expectation of this here minus something that is growing in t is greater equal to this right-hand side. The probability of N1 of t being smaller equal to the same right-hand side is really small. And we could write it out. We would get something that is exponentially small in t, in the number of remaining iterations. So that is really nice, because now we can define our algorithm, finally, and it's actually almost the same as the adaptive heuristic. The only change we're going to make will be down here. So instead of routing with a probability, we're going to set a hard threshold. Where previously we said with probability yi divided by expectation of ni of t, we now just say if it's greater than 1/2, do that. If it's smaller than 1/2, do the other. And we can.
Is it clear that one of the actions should satisfy this?
Great. So if we have, that's a fair question. Is it clear that one of the two satisfies it? If we have two actions, then yes, one of the two must be at least 1/2. If we have three actions, one of the three must be at least 1/3, and so forth. There will definitely have to be a constant. And in the proof over here, we didn't really use the 2 here.
Why don't you just say max of yi by expectation of ni?
Because I thought it was more instructive to go with the simpler example. But yes, basically, you want to go with the max. OK. We can then exactly bound the regret as we've done before. And we get something that's summable. So we get a constant bound on the loss that is incurred. Now, at this point, I do want to highlight that some skepticism might be in order. In particular, it is well known that if you think about the certainty equivalent LP at iteration 0, so think about just solving the certainty equivalent over the full time horizon, that it's well known it's impossible to compete with on a square, like to get a uniform loss with respect to. But that is not what we're doing. And this here is adapted from a 2017 paper by Wang et al. And I think this is instructive. So the certainty equivalent LP is too weak a benchmark. So it's too strong a benchmark. The gap here is too large. The offline, the clairvoyant, is actually square root additively away from the certainty equivalent LP. And that's what I drew here. So this is opt versus certainty equivalent. And what we show is that the profit algorithm that just thresholds is close to that, which in particular implies that opt is also close to that. And these here have been studied for slightly related problems for some time. In particular, Rayman and Wang got little O of square root of t, but still super constant for network revenue management, which we'll get to in a moment as also fitting into this same framework.
And what about expected LP?
Okay, sorry, let me be clearer. The certainty equivalent LP or expected LP would basically be the objective that we get when we solve the linear program, assuming that everything happens as an expectation. So
that is expected.
That's expected.
yeah, that is the expected LP. Now, that is, as a benchmark, too far away from what's obtainable. So on this plot here, what I did is I created a bunch of sample paths, and I evaluated the optimum, and I took the average of those optima for each time horizon. But then I also solved the expected LP, and I'm plotting the difference between the two. And you see the difference grows.
Yeah, sometimes actually you may need to have some additional things in addition of that. But we can get actually additive for profit using expected LP essentially. So I'm wondering why you cannot get the, maybe there are some additional bonds that you want to use it? You know, we can talk.
Yeah, sure. Yeah. Okay, so let's move away from our running example and think about what we actually used in this whole proof. One thing we definitely used was that our arrivals are concentrated around where we expect them to be. So I needed to use Höfting's inequality on the number of arrivals of each type. So this one is crucial. The second is I need my objective to only depend on the number of actions taken on each type over the full time horizon. For example, it's not clear that this works for discounting, where suddenly we say, if you take the same action on the same type in some iteration, the benefit is different from if you do it in a different iteration. And then we need two properties about the optimal solution. And if you synthesize it down, the real properties we need, one is simple. If we make few mistakes, we don't want to lose too much in our objective. And the other one, and that one's a bit trickier, we need the optimal solutions to be continuous in the arrivals. So if it was the case that as the arrival sequence changes a little bit, the optimal solution changes a great deal, then this whole proof idea wouldn't work, because then we wouldn't be able to track the optimal solution in the way the analysis does.
Doesn't the second one imply the first one?
This one here implies the under Lipschitz. Yeah.
You also need a bounded number of types of arrivals and decisions?
Yes. Yes. Possible to relax, maybe, but haven't figured it out yet. So here's a sufficient condition that turns out to be fairly general. Suppose the offline problem is to minimize a function f that is convex Lipschitz. So we can compute the fluid problem, so the expected LP or the expected offline solution. Lipschitz, so that a constant number of disagreements does not hurt the objective too much. And has the property, and this one is non-standard, that if we have an optimal solution for some arrival vector n, and we know that the real arrival vector n prime is not too far from n, then we want x and x prime. Then we want there to be an x prime that is optimal, that is not too far from the other x. So this is really saying, under perturbations of the arrivals, the optimal solution can change. It can change quite a bit. This is almost squared, the change in the arrivals. It cannot change too much. And the proof of sufficiency is basically exactly the same that we had before, except for the bound on the disagreement works slightly differently. This is a bit of a hand-wavy proof, but the idea is one of the actions needs to be linear in the remaining time horizon. This is exactly what you were asking, whether we know that one is at least 1/2. So finite number of actions means one of the actions is at least linear in the remaining time horizon. And then it must be exponentially unlikely that the arrival estimates are so far off from each other. So one example is fairly general class of linear programs. Basically, whenever you can replace your constraints by penalties, which turns out you can do for a lot of problems, this will work. And it's based on theorems from the 80s about the Lipschitz continuity of LP optimal solutions under perturbations on the right-hand side, meaning under perturbations in our case of the arrivals. Special cases of the LPs include bin packing, the problem that we studied today, this job allocation one. There's a really weird scheduling problem that I came up with that I'll be happy to admit is very contrived. Network revenue management, but really it is actually quite general. For bin packing, there's certainly a cheat in here, which is that we assume that the time horizon grows large, but the capacities of the bins are all constant. So we can enumerate over the possible configurations of what items go into each bin, and we can make each of these be one action. The scheduling problem, yeah.
Grows with the number of actions, right?
Yes. But not with the time horizon. Yeah. Now, extensions that actually work and are somewhat of interest. One, we don't really need the samples to be mutually independent. All we need is for them to be, let's say, sufficiently independent that they're going to concentrate. So mutual independence is actually much stronger an assumption than we need. Second, we don't really need to resolve every iteration because we only need to be sure in the proof. Okay, running out of time. In the proof, we didn't really need 0.5 to be the threshold. Instead, we could have chosen 0.25 and 0.75. And as long as we know for sure that between every 2 times that we resolve, the actions, the variables corresponding to the actions won't jump out of this interval, that would suffice. So we don't need to resolve every iteration. And this is one that I find quite interesting. We actually also don't need the exact distribution of the arrivals in each iteration. If we just have a single sample path of the arrivals over the full time horizon, that suffices. Let's skip the limitations. Those are negative anyway. And conclude. We have a simple sufficient condition for a uniformly bounded loss. The analysis is really quite simple. The meta message would be a threshold, don't randomize. And really important to get this right is to have the appropriate benchmark. If we had gone with the expected LP, there would have been no hope for constant loss. And we're still working on some problems where it's not as trivial to prove the, I want to say, the interesting property of F, which is this Lipschitz continuity under perturbations of the arrivals. Thank you. Happy to take questions or take them offline. Yeah.
Would your analysis work if the time horizon is randomized? If, for example, it's like not deterministic, not fixed?
Yes, as long as I have the right concentration on how much it's randomized by. So for example, we thought until 2 days ago that geometric works, and now we're pretty sure that geometric does not work. But if you give me some bounds on how far it varies, basically the only piece that we really need is that the number of arrivals of each type with high probability needs to vary by something that's sublinear. That is the key property.
Do you know what happens if you don't remember the amounts that were realized? All you remember is the number of times you went from 1 and from 2? Because it looks more like selective choice questions in economics.
I think you need the sum of the arrival. You need basically you need to know the state, but the state, I mean, for the specific problem, the state.
You don't need the order.
Yeah, you don't need the order. If you think about online knapsack, you wouldn't need to know what precise items you've allocated. You would need to know how much of the capacity you've used already. So that is sort of the general gist is you need to know only to the extent that it's going to affect your remaining decisions.